are back with skills from first year chemistry, and this is skills from first year chemistry 105. And what I'm talking about today are combustion analysis problems. And the two questions that were assigned to you for practicing this were the Zoomdall Chapter 3, questions 49 and 51. So before we get started with the example for the combustion analysis, I just want to keep a big picture. No, I'm good. It's all right. Just keep the big picture that these types of questions ultimately lead us to an empirical formula. So what you're going to see are some different types of empirical formula problems. And so I'm just going to kind of outline those first, and then we'll talk about the specifics of a combustion problem. So the first type of empirical formula problem is if you're given the molecular formula, then you just have to simplify with the largest common number, or largest common factor division. So that's one type. So as an example, if you're given a formula like C6H12O6, and this is the molecular formula, and you're asked for the empirical formula, you can divide by 6, and you would get CH2O as your empirical formula. So those are nice and easy. Thank you. Those are nice, easy ones where you just have to divide by the largest common factor there. Second one is if you are given percent by mass data. Or just given mass data. With these, if you're given the percent by mass, then you go through the process of assuming 100 grams of the substance. And this is what we talked about last time in skills from first year chemistry 104. So you assume 100 grams, convert to moles, and then you divide all the moles by the smallest moles. And then your quotients are your subscripts. Scoot that up a little bit. If you're just given straight mass data, so this is sort of a little subcategory. If you're given mass data, and that's a fancy way of saying grams, then you can skip the assume 100 grams part. And then just go directly to the convert to moles. No. No. I love you, but you're not going to be in the video. Thank you.
Sorry.
Okay, thanks. So the third type, there are 4. The third type is where you are looking at data from a combustion. And so with combustion analysis, we want to keep a couple things in mind before we get started with an example. And that is that this phrase or this word, a hydrocarbon, just means a substance that's made up only of carbon and hydrogen. So I put an X here and a Y here for the variables of the subscripts. So this is a hydrocarbon, and these are combusted produce the same two products every time. They produce carbon dioxide and water. So we want to keep that in mind, always producing carbon dioxide and water. Other substances also made of carbon, hydrogen, and oxygen, where you have CHO, when combusted.
You're doing great.
Also make CO2 and H2O. So just keep that in mind, that those products are always going to be carbon dioxide and water. And I'm going to flip to the next page here.
Good idea. So I'll be quiet.
Okay.
So
Thank you, Emmett.
you're doing good.
Thank you. Okay, so a couple more things that we want to remember before we get into the example of combustion analysis is that we can use the carbon dioxide produced to find the carbon in the original sample. And that could be mass or moles. And you're going to use the water produced to find the hydrogen in the original sample. And that could also be mass in grams or moles. Okay, so just as a kind of a big picture, keeping the big picture again, if we have our hydrocarbon, CXHY plus O2, we are going to produce carbon dioxide and water. The values of X and Y will determine the balancing of this, but what we want to remember is that all the carbon goes into the carbon dioxide, and all the hydrogen goes into the water. So we can use stoichiometry to figure out the amount of hydrogen and carbon in an original sample, and then work our way back to the empirical formula. Bless you.
Sorry.
So we can use stoichiometry to find carbon, hydrogen, and then if we need to, we can subtract to find oxygen in the original sample. Okay, and then last thing before we take a break and go on to part 2, and that is that there are 1,000 milligrams in every 1 gram. Or we could write 1 times 10 to the minus 3rd grams is 1 milligram. So that's something to keep in mind for these calculations, because often the values are given in units of milligrams. So we'll stop there and give you a rest, and then we'll come back with an example of like a level 1 combustion analysis problem, and then we'll take a break, and then we'll do a level 2 analysis combustion problem. Thank you.